Okay, good afternoon. First, I would like to thank organizers for the work they are doing. So it's really a pleasure and opportunity to discuss with you this topic. And even I have also privilege to present some very recent theoretical result related to this topic done by Valery Vinokur and collaborators. So I will, because of the short time of presentation, I will just skip introductions that sometimes is useful, and go directly to the point. Actually, today you already have seen this phase diagram introduced more than 2 decades ago by Matthew Fisher, discussing various transitions in two-dimensional superconducting system. And I'm just ignore this finite temperature possibilities. And you can see two quantum phase transition, the quantum because it's zero temperature transitions, as a function of either disorder, which in this context of the transition is nothing but just disorder-driven unbinding of vortex-antivortex, and possibility of magnetic field, externally applied magnetic field, from superconducting state or vortex glass if you introduce just quench disorder, and transition to insulating state related to Bézère-Einstein condensation of the vortices, because vortices are bosons. And idea was exactly that, and just in the vicinity or just at the critical parameter epsilon c that can be applied magnetic field disorder, could be electric field carrier density in this studied films and so on. You have uncondensed both Cooper pairs and uncondensed vortices. But this is just at the critical value of the critical parameter, and just above of that you expected insulating state of superfluid vortices. Well, and this is actually scaling what was proposed by Fisher. It works and was confirmed in quite many systems at high enough temperatures. And these results, I could present and show for sure much more results, and I just not discussing here who was first to measure. My feeling is that Art Hebert was one of the first, but in indium oxide film. But anyway, you see the scaling, what Matthew Fisher suggested is quite work well. And what's happening at low temperatures, you can realize that scaling is not so good. You see just this dotted line go away from the all other branches, which are scaled well. And this is also clear from the plot on the just measured resistance as a function of temperature or inverse temperature, that the resistance just saturate. And in more recent times, it was observed already not for superconducting films which are disordered, and we heard today nice presentation on that. Once again, I can put more reference on that, but this is just for illustration. This is a recent paper for niobium-selenium-2, and you see a saturation of the resistance at low temperatures, whose origin is under discussion. And this is what's called some sort of quantum metal states. And this is actually a central point which I try to just discuss and bring to your attention. Okay, the question often happens, how do often this and this behavior? Because many results it shows only high temperature part, of the measured curves. But if you really look of the more results which are measured at low enough temperatures, even in strongly insulating regime, this is a transition for gallium film as a function of thickness, and you can translate it in the, as a function of quench disorder. You see the tendency of saturation at low temperatures, also in the lead films, and various experiments in Josephson junction arrays for values of the Josephson energy and Coulomb energy comparable. You can drive it by applying the magnetic field. In this case, it's just the a fraction of the magnetic field for a cell of the Josephson junction array. And once again, you can see this feature of saturation of the resistance, both sides superconducting-like and insulating-like state. Well, this behavior was discussed also in the last at least decade, maybe even slightly more than just decade. And basically we can understand the question, what was nicely illustrated in this cartoon by Philip Phillips and Denis Dalidovich. And you can see two possibilities. Just think on the Heisenberg uncertainty principle apply to superconductors, granular superconductors, or Josephson junction arrays. And when you have to totally localized Cooper pairs inside of the grains without possibility to transport between the grains. In other words, you have 100% certainty that you will find all the Cooper pairs localized within the grains. You have infinite uncertainty in the phase. In other words, you have the superfluidity of vortices. So, and just opposite, when you have this possibility, the Cooper pairs transfer, and you just have this, for instance, pinning localization of the vortices, you have the zero resistance state. That's it. The questions that what they discuss on the possibility quantum metal or Bose metal state, in the sense that keeping hot core, hot boson description of the situation. And they introduce just disorder, trying to show that there is intermediate phase, and not only at the critical value of the parameter, like in the Fisher's theory. It was several works done by Seb Donig and his postdoc Das, related to the same problem, but what was added more is, and it was not included in the Philip Phillips description in the model, is transverse gauge fluctuations starting again from Josephson junction arrays. And they proposed two-parameter scaling. This two-parameter scaling is just, completely empirical. There is no rigorous theory like result of the one-parameter scaling of Fisher for vortex glass insulator transition. But this is scaling imply possibility of intermediate phase, exactly as I already mentioned, between the superconductor and insulator. And this is physically understand this state you can introduce in the gauge fluctuations, which basically, according to the authors, will lead Aharonov-Bohm phase, and even lead to transmutation from Bose and fermion direct statistics. In other words, removing the bosons from the condensate, and which will preclude the infinite resistance state for both sides of the transition. Okay, and this is a result what was recently, and this is unpublished result, which again done by this authors, Valery Vinokur and collaborators, and basically starting, and this is not published result, and even I didn't see a manuscript, okay, but after discussion I realized that this is rigorous calculation starting from Josephson junctions array picture and also introducing the transverse gauge fluctuations. And you can see that this is some dimensionless parameter which measure the strength of gauge fluctuations, and you have the one critical point, which is again the Josephson energy and Coulomb energy comparable, and you increasing further the gauge fluctuation, you come to so-called the quantum metal, and I would say the boson metal, when you have both Cooper pairs and vortices uncondensed. Well, applying to experiment what was done by Cydonia, you can see how you can really make the good scaling, and in spite of its empirical scaling, and very difficult to make some far going conclusions, but at least the transition which account this scaling can account the saturation resistance in a low temperature, and this is critical exponents what they obtain. Actually, another message, but related, and this is actually what brought us to interest to semi-metals. This is one of the reasons which about 15 years ago we started interested in semi-metals, and you can see the similar metal-insulator-like transition in semi-metals. If 15 years ago I would say both graphite and bismuth just simple non-topological semi-metals, but today we know that this is not true, at least for bismuth, that this is not true. But what I will show that it's probably not a crucial point if it is Dirac or Weyl or just trivial semi-metals, or maybe just a very small or zero effective mass, but actually it's not good to say effective mass zero, but let's say, or you describe the Schrödinger equation with very small effective mass, or you apply the quantum electrodynamics and Dirac equation to describe that. For such a system, it seems this scaling works perfectly. And I don't know what's the reason, but once again, we can fit quite well with the exponents what Donia used for molybdenum germanium films, but the best fitting we got using this exponent. And this is maybe just accidentally, but very close to exponent known as a quantum percolation exponent. Once again, I am afraid to make far-going conclusions. And just to exclude and maybe at least think about this, that this could be not transition and just a matter of Drude transport can be well explained. The physics or related theories and just include 2-band or 5 bands or maybe more. I just showed the result of similar transition in graphene, this from Princeton group, and making analyzing this metal insulator transition, this conductivity. So you go to insulating states from top to bottom, and you see similarities quite impressive with bulk graphite and graphene in this case. So multi-band picture, it seems it's difficult to employ. And again, make all this story long but very short. I just, for illustration, show some of selected semi-metals, which some of them topologically non-trivial. or some of them trivial. And basically they show the same kind of transition. It could be, by the way, not only field-induced, it could be disorder-induced, could be pressure-induced transition, and the same two-parameter scaling works pretty well. And what is more probably, how to say, indicative, that all of these materials are very close to superconducting instability. Once again, this list of these semi-metals which are just transformed to superconducting state can be increased drastically. But some of them, starting from black phosphor, because it was several decades ago, more recent results, and very recently even in bismuth single crystal, but temperature is extremely low. But anyway, all of them show the tendency to superconducting correlations. And once again, 10 years ago, we make this comparison between bulk bismuth and magnetization. The signature is really very, very tiny. But it's not surprising if you associate the superconducting correlations with the surface, which is not unplusable. And the scaling, once again, Bose metal-like proposed by Das and Doniak. And you see the losing of this diamagnetic activities with field and the critical field roughly coincide with the critical field for bismuth is around 500 Ersted. Well, and what about all that? I just would like to ask questions. When we're discussing like pseudo-gap phase in cuprates, what we are talking, we know that if you make the optimal doping, you go to superconducting state. When you go away, you just lose superconductivity, and you have the pseudo-gap state, and you have in the underdope regime. But you are sure that you can talk about superconductivity because you measured superconductivity at optimal doping. But now we are starting, suppose that you start exactly from the opposite side, and you need some special parameters with the systems which not only doping, but as I showed for semi-metals like a pressure or maybe other modification of the material, but still we can discuss in the same physical picture. But I should admit that this only the scaling and some signature of superconducting activity, what I show, allowed at least make the hypothesis or propose that a similarity in the behavior of pseudo-gap phase and the apparently normal states of the system which present Bose metal insulator type scaling transition. In other words, what is the pseudo-gap state according to Phil Anderson? That this is just enormous extension of vortex liquid. In other words, you have still the Cooper pairs which tight bonded, and you have vortex liquid and in between. The only parameter what you need to introduce to make sense of this discussion, some sort of incompressibility, and this is should be already a special discussion on the origin of this phenomenon. And I think I already almost done. Leaving some time for the questions. And instead of conclusion, you can just read what's written here, and actually more, not more, much more evidence, experimental evidence for existence of tight bonded Cooper pairs in materials like bismuth or other semi-metals, which are close to superconducting instability, will help or clarify if it's validity of this physical picture which I presented today. Thank you.